4. So that's me. That's me presenting. That's me presenting. So I'm happy and proud to present the speaker of Work Group 4. We have Dima Shaiderman. He's studying for his PhD in the School of Mathematical Sciences of Tel Aviv University, where he did his previous degrees under the supervision of Ehud Lehrer. He has a very nice paper in MOR about a new characterization of exchangeable processes in terms of posteriors, but I think today is going to talk about something different, and I'm curious to hear. So Dima, the floor is yours. You're a co-host. Please go ahead.
Thank you, Gali. Thank you very much for this opportunity. Today, we will talk about repeated games with incomplete information on one side, with some new class of dynamics, predictable ergodic ones. This is a joint work with my advisor, Ehud. And to start, let us review briefly the model of repeated games with the incomplete information on one side, which was first introduced by Aumann and Maschler in the 1960s. So we have 4 parameters to the model. We have a finite set of states denoted by K. We have a probability distribution over those states, P. We have I and J, finite sets of actions for players 1 and 2 respectively. And we have a scalar function which assigns to every state and pair of actions a scalar. So this will be a zero-sum game. And let me introduce the n-stage repeated game, gamma n of p. So this game will be a zero-sum game with incomplete information, and its play will proceed by steps. So at the first step of the game, nature will choose some state k according to the distribution p. Player 1 will be informed of the chosen state. Player 2, however, will only know the distribution p. At every stage n, small n, both players will choose simultaneously actions in and jn in their action sets, and those pairs of action will be publicly announced. And in the end of the game, the total payoff to player 1 will be the average per stage payoff along the game. Okay, so one question which one can ask is how does the value of this n-stage repeated game behaves when n tends to infinity? And this is the first part of Aumann and Maschler's seminal Carville Theorem. So to state it, let me first introduce the non-revealing game. So for every state, we define a zero-sum matrix game, GK, which simply fixes the first coordinate of the payoff function G to be that state K, and we go over all pairs of actions available to players. And we denote by U of P the value of the zero-sum matrix game in which we take the weighted average of those matrices GK with respect to the probability distribution P. So if we denote by Vn of P the value of this game, their seminal theorem states that the limit as n tends to infinity exists, and moreover, it equals KV of P, where KV is defined from the simplex of probabilities over K to R, and it is the smallest concave function greater or equal to U. So here we see a simple example. To prove this result, Aumann and Maschler introduced many new techniques, one of which is the technique of splitting, which gives an exact recipe for player 1 as to how, when, and how much to use his information. So let me give a very short example. We look here at the graph of the function u of p, and we look at this point p. This is a point at which the graph attains a local minima. And let us assume that P can be written as a convex combination with weights alpha and 1 minus alpha of these two points, PL and P right, so that the concavification of the function at point P just equals the same weighted average of the function U at the points P left and P right. So player 1 can perform an information-dependent lottery X, so that the posterior probability to the state K1 under X will just depend on the outcome of X. If X is left, the posterior will be P left, and so for the other case. And moreover, the distribution of the lottery X will follow the weights in the convex combination of P in terms of P left and P right. For the analysis of player 2, they introduced the notion of martingales of beliefs, used the minimax theorem, studied and defined the non-revealing game. And 40 years after Aumann and Maschler's seminal result, Renault looked at a more general problem from a dynamic standpoint, where he added an additional parameter to the model of Aumann and Maschler, and that is a stochastic matrix M over the state space K. So this is a matrix with non-negative entries, so that the elements in each row sum up to 1. And he once again considered an n-stage repeated game, this time depending both on the prior P and on the matrix M, in which we look at a stochastic process, an n-step stochastic process that follows a Markov chain with initial P and stochastic matrix M, so that at each stage, small n, player 1 is informed of the realized value of the Markov chain. Again, both players choose simultaneously actions, IN and JN, which are publicly announced, and the total payoff to player 1 will be once again the average per stage payoff, only that notice that this time at each stage, the state evolves stochastically, according to the chain. A big difference between the models of Renault and Aumann and Maschler is the information that player 1 has to deal with. You can think of the information in the Aumann-Maschler model as being a static one, namely player 1 is informed at the start of the game of the chosen state, and that's it. He has nothing else to learn. Whereas in Renault's model, there is a constant stream of new information for player 1 that he has to take into account on the fly. And in 2008, Neyman was able to construct a beautiful reduction from this dynamic information to a more static information, and he did it using a tool from probability theory that sometimes is being referred to as a real-time transformation, where he changed the Markov chain to a closed process, which can be embedded in a more general model of Aumann and Maschler, in which the stage game are played in extensive form. Renault's theorem, once again, the first part of it deals with the existence of the value of the limit of the n-stage values as n tends to infinity. And here again, this limit exists, and it equals the concavification of some function w, which corresponds to a new non-revealing game Renault defined and studied, evaluated at P times some stochastic matrix B0, where B0 can be attained as the limit of the transition matrix along some arithmetic progression of powers. And in this work, we want to maybe give a more general framework to the dynamics aspect. So we just fix a stochastic process psi. This is a discrete time process on some probability space, and we assume that its steps are supported on a finite set K. This set K will be the set of states of the game. And once more, I and J are the finite sets of actions available to players 1 and 2. And G is a scalar function that assigns to each state and pair of actions a payoff. Consider now the infinitely repeated game, which depends on this process. And this game will be played by steps. So at each stage n, player 1 will be told the current realized value of psi, that is psi n. Both players will continue by choosing actions in their own set of actions, which will be publicly announced. Okay, what will be the final duration payoff in this case? So as before, for every pair of strategies, sigma of player 1 and tau of player 2, we can look at the expected per stage payoff, where we take expected value over both the strategies and the process. And this game is a finite game in extensive form, so we can denote its value by Vn of psi. And an important asymptotic property that is studied in these infinitely repeated games is the notion of the uniform value. So this will be a scalar, and it will be said to be the uniform value of the game if two conditions hold. The first of which is that player one can guarantee it, namely for every epsilon, there exists some cutoff n epsilon and the strategy sigma epsilon, so that for every duration above this cutoff, player one can guarantee at least v infinity of psi minus epsilon against all strategies of player two. And the dual condition for player two is that for every epsilon, there exists some strategy tau epsilon of player two, and the cutoff, so that for every duration above this cutoff, the payoff at the game with this duration will not exceed this uniform value plus epsilon against all strategies of player one. So let us now complete the theorems of Aumann, Maschler, and Renault. Let psi of AM be the Aumann-Maschler dynamics, namely every step of the process agrees with the first step. The seminal Carville theorem states that the uniform value exists and it equals to the limit of the values of the finite duration games and to Carville of P. And let psi of R be Renault dynamics, in which the process follows a Markov chain, and a parallel result holds as well. There exists a uniform value, it will equal to the limit of the finite duration game values. An important property that plays a key role in Aumann-Maschler is the stationarity. So this is actually a gift that this model allows. Let us assume that psi is some stationary process, which means that for every event A, which is Borel measurable under the product topology over the state space K, the distribution of the entire process is invariant to shift in times. And thus, if player two patches together his optimal strategies in the n stage game, and then in the m stage game, we will get the following inequality. The value of the m plus n stage game times m plus n will be non greater than n times vn plus m times vm. And the stationarity here allows this because player two can play whatever he wants, forget about everything he saw, and then play again optimally in some game, and the dynamics will start over. This implies that the sequence of scalars n times vn is subadditive, and by calculus we know that this guarantees that the limit of the finite duration games of their value exists. So we got it for free that this limit exists, and moreover, player two can guarantee it by just patching together all of these finite duration games optimal strategies one after the other. One may ask thus, is it true that for every stationary dynamics, the uniform value should exist? And to start answering this question, we need to find some pool of stationary dynamics. And one of the biggest pools for such dynamics are measure-preserving systems. So let us consider the circle, the Borel sigma algebra on it, and Lebesgue's measure. And let us define the transformation T alpha to be the irrational rotation of the circle by the irrational degree alpha. So here we see the picture. And an important properties of this transformation is that, first of all, it is, of course, measurable. And the second property is that it preserves measure. This is actually a property of Lebesgue's measure, which holds in this case. And this is just an example of what is called the measure-preserving system. So in general, a measure-preserving system is a four-tuple. It consists of a probability space and some transformation from the space to itself, such that the inverse image of every measurable set is measurable, and the measure is saved under reverse images of the transformations. Let me give a further definition. This system will said to be ergodic if for every two events having positive probability, there exists some positive integer n, so that when we take A and intersect it with a shift in time n of B, we will get an event of positive probability. So an example of ergodic systems is the rational rotation I just described, and to those of you who are familiar with it, the cut and stack system. Now, how can we get from these systems to a stochastic dynamics? So just we need to consider partitions of such systems. So here is a simple example. Let us look at the partition of the circle to the northern and southern hemisphere. And let us define now pointwise our sequence of random variables. So the first random variable will just indicate if the point is in the north or south. And for every n greater or equal to 2, the n step of the process evaluated at x will indicate if after we rotate x n minus 1 times, we will end up in the north or the south. So here, x at the beginning is in the north, so the first step is 1. After we rotate it 3 times, we are in the south, so the fourth step of the process will equal 0. And this will be a stationary process. Back to game theory, from player 1's perspective, he just sees a binary sequence of realizations, and he believes that this point x was chosen from the circle randomly according to Lebesgue's measure. In the same fashion, we can consider any finite partition of such systems, measure-preserving system, and we can define stationary processes that are generated by this partition by the following formula, which in word just means that the nth step of the process evaluated at x will equal j if and only if t n minus 1 of x will lie in the jth element of the partition. So this is just the parallel construction to what we see seen on the circle. And when player 1 observes this process, he learns something. So actually in the circle, he gets geometrical information. If he saw, say, the history 1 and 1, he knows that he is in this arc. And overall, there are 4 possibilities that he can know after 2 steps. After 3 steps, there are 6 information steps, sets that correspond to the different histories. And because alpha is irrational, then we actually know that for every n, there are exactly 2 n information sets, which become of arbitrary small measure as n goes to infinity. Okay, so these arcs become very, very small. Let us assume that some time in the process have go on, and we have here in. This is the information of player 1 after the n step. Let us define x to be the middle point of this arc, and rho to be the radius of this arc. And let me draw 2 danger zones near 0 and near half. And I call them danger zones because whenever the point x is in those zones, we know that at least 2 different points in the arc in would lie on opposite sides of the equator. So if all player 1 knows is that the true state of the world is in in, whenever x visits here, player 1 could not tell for certain whether he should see 0 or 1. This is not the case when the rotation puts us outside of the danger zones. Then player 1 will know that the L+1 step of the process will be constant on in. Yes, so it takes only the information in the n step, and it can already project very far to the future. And the question is, how often will x visit those danger zones under the rotation? And well, this is the ergodic theorem, that it will occur exactly at the measure of these 2 danger zones, which is 4 rho. And 4 rho itself will be a very small probability event as in will become smaller and smaller. So to summarize, whenever the information is refined enough, player 1 could predict more and more accurately into the infinite future the steps of the process outside of some times in which he will be in the danger zones. So based on this definition, based on this observation, we defined the asymptotically predictable ergodic systems. And here I give only an informal definition. I'll spare you most of the details. So an ergodic system is asymptotically predictable if for nice and dense partitions in some sense, like say partitions to unions of arcs, the process that are generated by those partitions satisfy that if after n steps, the realizations at point x and at point y are close in some sense, agree most of the time, then the infinite realizations at point x and y will also be close for most of the time. And once again, two examples for such systems is the irrational rotation and the cut and stack, to those of you who know. Let now fix a general partition of this system. This should not be a nice partition. It can be as general as you can think. We once again consider the stochastic process that is defined by this partition. So in the n step, once again, the process at point x will equal j. If when we take the n minus 1 mappings of x, we will end up in the jth element of the partition. And for this process, I claim the following. In words, after observing the first capital N steps of Xi, I can predict with high probability, at least 1 minus epsilon, all future steps of Xi at an average success rate, which is high in it of itself, 1 minus epsilon. And formally, for every epsilon which is greater than 0, there exists some cutoff N and the sequence of random variables y, such that every step of the process y is measurable with respect to the first capital N steps of the process Xi. And moreover, when we look at the event in which the lim inf of the frequency of times at which the two processes coincide, and we look at those points in which this quantity is greater than 1 minus epsilon, this event will have probability at least 1 minus epsilon. So this means that the prediction will be better and better with time. What does this mean for player 1? This means that the essential information to player 1 is in which one of the positive probability elements of the partition that generates the first small n steps of the process, the point that was chosen lies. So this is just as we've seen before, but this time we look after n steps. These are the possible information sets. And whenever player 1 is in one of those states, he knows pretty much what will happen in the entire future. So let us now recall that this is very similar to Aumann and Maschler, right? Because in their model, you learn an information and you know now from this point to infinity what will happen. The main difference is that the stream of states that follows this information set need not be constant. It can be very, very chaotic, especially in the irrational rotation system. And this is, of course, on one hand, good, because when we have finitely many information sets, we can split the beliefs of the opponent. But because this sequence is non-periodic, it is not clear what we can guarantee with the split. We don't have a closed formula, and we don't have a closed formula for the limit of the n-stage values as well. I mean, at face value. So we want to split, but we don't know whether it should equal the limit of Vn, and the limit of Vn only bounds the uniform value from above. So there is some work to be done to understand. But the main theorem of the paper, our main result, is that whenever we fix such an asymptotically predictable system, and we consider stationary processes generated by finite partitions of such systems, the uniform value must exist, and parallelly to the results of Aumann, Maschler, and Renault, it will equal the limit of the n-stage values. So a nice application of this result is a new limit theorem for such systems. So let us consider again an asymptotically predictable ergodic system, and let us take a partition of this system to two events and consider the binary stationary process generated by this partition. So we claim that there exists a triangular array T, such that two conditions hold. The first condition is that if we look at those information sets and we shift every one of them at the corresponding time described in the nth row of the array, we will get in their intersection a probability, an event of positive probability for every n. And the second property is that if we look at every row of this array and we look at the steps of the process evaluated at these times, and we take their average, their weighted average with respect to the probabilities of these information sets, then this will be a random variable, and it will go to the expected value of the process in L1. So to conclude the talk, let me just say that the general problem concerns the existence of the uniform value on measure preserving ergodic systems. And thus far, we know that the existence holds in the Aumann-Maschler case, in Renault's case, and in our case. And of course, it is interesting whether it exists in other dynamics as well. This is it.
Thank you, Dima. We have some time for questions. I'm sure there are questions.
May I ask one more question? I'm sorry for you had a slide with an informal definition of predictability, and it had you had an additional property. Yes, that they generate satisfy. So this capital N, what does it depend on exactly? Is it an epsilon type of definition for that for every epsilon you have an N? So it only depends on the epsilon and not on the observations until
no,
N, right?
It depends. It depends both on the epsilon. It depends on some measurand C, which bounds this difference between the two lines, and also N may depend on the process as well, on the partition.
Okay.
So, but this is a very long and not so elegant definition.
Right. But the capital N doesn't depend on the values of xi at time 1, at time 2. You can say you know N beforehand. Okay, thanks.
Any more questions?
Dima, do you mind me asking a question? Got it?
Yes, please.
Sure.
So it's Arkady speaking, by the way. So thanks for your very interesting talk. If capital T is the backward shift, and X is some symbolic space, what kind of partition would be good for your theorem?
So we don't know. I mean, we cannot say almost anything about general systems, or if you call about Z, we can say almost anything about taking the transformation back in time. I mean, I presented only what is known to us.
Okay. Then thank you for this presentation. Thank you. Before we take the 15 minutes break, let me just thank